Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello? Yeah, okay. So a few people standing outside, but I think we can start, they'll come in. So our speaker today is Rahul Jain, and I think he graduated from University of Berkeley in EECS department in about 2 years ago, and now he's a visiting scholar in the same university, and he will be talking about combinatorial market design for efficient resource allocation.
Well, Kamal, thanks a lot for the introduction, and it's a pleasure to be here. And so I'm going to talk about market design for efficient resource allocation. And in particular, the focus of this talk will be on markets which have a combinatorial structure, such as those which occur in networks. So what I'm going to do is I will start by talking about introducing two our problems of resource allocation which arise in networks, and then we'll see relevant notions of efficiency and equilibria for such problems, and then I will introduce a market mechanism which can be used to solve such resource allocation problems, and then we'll see some equilibrium analysis, and then finally some experimental results. Okay, so let me start with the caricature of the internet. So the internet is really much more than a network. There are various domains such as the AT&T network and the MSI network and the Sprint network, and then there are entities such as AOL and Comcast, and so it's really a complex, very complex system, and it's a network of networks, and each of these entities owns a part of this very complex system, and it has its own information about the state of the system as well as its own objectives. But it's really their interaction together which determines how this whole system as a whole operates. And so a question then is, how can we devise mechanisms such that these entities, each of them acting independently and in their own interest, still end up achieving some system objective? So let's keep this fundamental question in mind, and let us look at a toy resource allocation problem at two different levels. So let's say we have a single link network, and there are two users, and so these users send traffic on this single link network at a certain rate, and if they send too much traffic, then of course they will cause congestion. Now to control congestion, the network could send back a pricing signal which could be a function of the amount of congestion cost, and then these two users, depending on how much, what utility that they derive by obtaining a certain flow rate on this in this network, they would adjust their flow rate, and in this way, the network, even though it doesn't know what the actual utility functions are of the two users, it can obtain a certain allocation of resources between them. And one could say that that's depending on what kind of algorithm we have used, one might be able to achieve an allocation of resources between them which is optimal in some sense. And one particular objective could be just the sum of the utility functions of the two users. So what's happening here is that the pricing signals here are being used to decompose this flow optimization problem, where the users solve a primal problem and the network solves a dual problem. And it was discovered that one could view the TCP network interaction as solving essentially such a problem in this manner, and this led to a fairly deep understanding of how and why TCP works. And one thing that came out of this line of work, there's been a fair amount of work along these lines, is that now we can say that we have fair bit of confidence that any internet instability is unlikely if most of the users use TCP, the TCP protocol or some variant of TCP protocol. So, so we can say that that resource allocation at this very fine-grained user level is largely a solved problem. And but now the question is what happens at a more macro level.
So wait, what do you mean by most users use TCP?
Well, there are
I could selfishly sort of do something different what the TCP tells me, and you will never charge me. Right?
But sorry, I'm not very precise. But what has been shown is that if there are users who are using different versions of TCP, then the internet would still be stable, in the sense that the queues at any router in the internet would be finite. They wouldn't become unbounded with time. I'm not very precise because that's not what the focus of this talk is going to be, but that's what I mean. Yeah. Okay. Okay. So now the question is, okay, so we have a very good understanding of resource allocation at this fine-grained user level, but what about resource allocation at a more macro level, where there are carriers such as AT&T, and then there are service providers such as AOL, and these interact. So let's consider the following setting. So let's say we have, this is the internet backbone, and there are carriers such as AT&T and MCI and Sprint who own parts of the internet backbone. And then there are service providers such as AOL and Comcast and Earthlink who would like to obtain capacity on various links to construct their routes and their networks and provide service to their customers. The carriers, each of these carriers is independent, and they have their own business models and their own cost functions. And on the other hand, these service providers, depending on how much traffic they're able to carry on their network, they would derive a certain utility. And this utility function is private information. Now, from a system project perspective, our objective is to determine an allocation or an exchange of resources between these carriers or network operators and these service providers, such that, let's say, what's called the social welfare is maximized, which is the sum of utility functions of the service providers minus the cost functions of the network operators.
Traffic is allowed to be split, or it should be only on a single path?
Let's say it can split. So right now we don't impose any restrictions on what we can do with that. So this is the question. This is the problem at a very high level. So now the problem is that for a system designer, these utility functions and these cost functions are not really known because they are private information. And so then the question is, what kind of mechanisms can we devise such that all these entities acting independently and in their own interest would still end up achieving this system objective? So that's the goal. Okay. And one thing I would like to mention here is that even though I'm presenting this problem in the context of a network, but at an abstract level, that's not really crucial here. And we'll see that in the problem formulation later. Okay, so let us now see how such a question can be addressed and what are the right notions of efficiency and equilibria to consider. So let me start with a very basic, some basics from economics. So let's say we have one good, and this could be capacity on a link in a network. And let's say we put a price P on this good. And given this price P, let's say a buyer I, So a buyer I demands DI units, and a seller J at this price demands some SJ units. Then given these demand functions and these supply functions, we can obtain the total demand as a function of price and the total supply as a function of price. And let's consider this price with total demand equals total supply. And let's consider an allocation where a buyer I gets exactly what he wants at this price, and a seller J gets sells exactly what he's willing to sell at that price. Okay, so such an allocation and prices is called comparative equilibrium. And now a fundamental theorem of welfare economics says that a comparative equilibrium is such that the corresponding allocation is what's called Pareto efficient. And what that means is that this allocation cannot be changed to make any agent better off without making any other agent worse off. And moreover, in a certain environment, this allocation also maximizes social welfare. And so what that means is that if by magic we can determine comparative prices and we could impose these on the goods, then each of these buyers and sellers would demand or supply exactly the allocation which maximizes the social welfare. So it's a very desirable outcome. Yeah.
Who chooses the prices?
So far we're not getting into the mechanism of how these prices are determined, but right now I guess the next step I'm going to consider is the existence of such prices, and then we'll worry later about how such prices might be determined. Okay, so now let us. So now the question is, does a comparative equilibrium always exist? And we would, and particularly in the case of a network. So we're interested in that particular question. And to answer that question, let's look at an example. So let's say we have a 3-link network, and there is capacity 1 on each link, and this capacity is indivisible. And there are 4 users, and so users A, B, and C, they want routes consisting of 2 links, and user D wants a route consisting of only 1 link. And if user A, B, C get what they want, then they derive utility 1, otherwise they derive utility 0. And user D, if he gets capacity 1 on link 3, then he gets utility 0.1, otherwise he gets utility 0. Okay. So now the question is, can we, yeah, you have a question? Okay. Now the question is, can we find prices P1, P2, P3 on these links such that each user gets exactly what he wants at those prices, and moreover, capacity on every link is allocated to some user. So if we can find such prices, then those prices will be comparative prices. So we can write down the conditions for that, and we get this set of inequalities, and it turns out that there is no solution to this set of inequalities, so a comparative equilibrium does not exist in this case. So this is a, yeah.
How is this notion is related to what's called the truthful mechanism or competitive incentive mechanism?
So right now, these players are not strategic. So they're not going to try to manipulate the allocation. So a price is announced, and they just respond to that price, depending on their actual utility function. That's all.
Yeah, so that means that they don't.
But I will get to that later in the talk. So at this point, the first question I'm trying to address is the existence of comparative equilibrium. And so So this in fact is well known that a competitive equilibrium does not exist in a market with the indivisible goods. And what I have done here is we have a counterexample in the context of a network which shows that it doesn't, that competitive equilibrium does not exist. And there's nothing new here.
You could split the capacity between the users,
then competitive equilibrium will exist. Though it does depend on, it turns out that in this particular case it will exist. Yeah. So I will come to that next, actually. That's the next fact. So the so one of the funny things about this particular example is that the network here is very special, and that suggests, and in particular it has a cycle. So that suggests that maybe the existence of competitive equilibrium might have something to do with the network topology. And it turns out that indeed there is a connection, and in particular if the utility functions are linear and the network is totally unimodular, that is all the routes lie on a spanning tree, then one can argue that a competitive equilibrium will exist. And this fact is also fairly simple for those who work on approximation of integer programs. They should be quite apparent that this is true.
I don't quite understand what does mean all the routes lie on a spanning tree. So it means your network is a tree or not?
Yeah. So network need not be tree, but if you consider all the users and look at all the routes that they want, then that should be a spanning tree.
Why so?
That's just a condition. So if this condition is true, then
so what do you do with suppliers who sit on the non-spanning edges?
In that case, a competitive equilibrium will not exist. So that's the problem I'm going to address next. So this only gives conditions when you might expect a competitive equilibrium to exist.
So you're saying that both the guys who supply capacity and the guys who want to eat capacity only lie on a spanning tree?
Well,
I don't quite understand what it means that all the routes lie on a spanning tree versus the network is a tree. Okay,
so let me just step back and then say where this is coming from, and then I'll answer your question. So where this is coming from is that if you formulate the problem of so essentially the flow optimization problem, then that will be an integer program. Now if you look at the linear programming relaxation of that, then that is guaranteed to have integral solutions if the constraint matrix is totally unimodular, and that's where this is coming from. If you have buyers and suppliers such that the constraint matrix is totally unimodular, then this will be guaranteed. And this also relates to the other question, that what happens if the capacity is divisible. So in that case exactly. So it will be a linear program, and it will have a solution, and the dual variables will be the solution of the dual will be comparative prices. But from here I'm trying to go to another step, and which is what happens, what can we say when the utility functions are general and network has a general topology. So from this counterexample, we already know that in general it is not going to exist. But now the question is, can we say something about achieving approximate efficiency or efficiency when there is asymptotically when there is a large number of users? And when there are a large number of users, then there will be condition of sort of perfect competition, and there are various models of perfect competition. So I'm going to consider a particular model, and let's say we have L indivisible goods, and these could be L links in a network, and there are capacities C1 to CL which are indivisible, and there is enough liquidity in the form of some currency of money. And let's say that we have a continuum of agents such that for every real number between 0 and 1, there is a buyer, let's say S, who at prices P on the goods demands DS units of some bundle of goods RS, and this could be links that constitute a route. So that's the crucial thing here. So now this demand is for a bundle. And similarly, we'll say that for every real number between 0 and 1, there is a seller who at prices P is willing to offer up to ST units of some set of goods LT.
Are you making any assumptions on D and S?
There are no assumptions, no. There are some very mild assumptions, but I'm not assuming any continuity or convexity.
Oh, other than continuity?
No. Well, there are some mild assumptions. Yeah. There are some assumptions on preferences, but they are very, very mild. And now, an allocation and prices such that total demand equals total supply, and moreover a buyer gets what he wants at those prices, and a seller is able to sell what he's willing to offer at those prices. This would be called a competitive equilibrium. Yeah. Well, these are correspondences actually. Yeah. So there could be other points, but as long as 0 is in there, we'll call it a competitive equilibrium. Yeah. So ds is a correspondence, and then this here is integral of a correspondence. Yeah. So this particular model of perfect competition, so this was introduced by Aumann, and he in fact proved the existence of competitive equilibrium for such a model, but when the goods were divisible. And so here we extended that result to the case when the goods are indivisible. So there's a lot of detail in the proof. I'm not going to go into the details. So essentially one has to formulate this problem as a fixed point problem and show existence of fixed point, but it relies on a very cute result due to Lyapunov, which says that the integral of any correspondence with respect to a non-atomic measure is closed and convex, and that is the key thing that is used here. So one very natural question at this point is, okay, so there is really no real economic system or no real market which can be thought of as a continuum model. So what is the utility of such a result? And it turns out that now one can show existence of various kinds of approximate competitive equilibria in a finite case, and where such competitive equilibria are of the following kind. So where total demand may not exactly equal total supply, but almost does, and moreover not every agent gets what he would like to buy or sell at those prices, but the fraction of agents who are not satisfied is negligible. Oops. Okay, so this result now gives us some hope that maybe we can find mechanisms which we might not be able to achieve efficiency, but at least they achieve, maybe we can find mechanisms which achieve approximate efficiency. So let me now introduce a market mechanism, and then we'll see what kind of properties it has. So the setting here is that again we have L indivisible goods, and there are buyers, and these buyers want bundles of goods, and in the network case, they would want bundles of links which constitute a route. And the sellers here offer individual goods. So they can offer multiple units, but they offer individual goods. And so what this mechanism does is that it elicits information from the buyers and sellers indicative of their demand and supply functions. So for example, a buyer I would report that he would like to get up to delta I units of some bundle of goods Ri, and is willing to pay Bi dollars per unit when his true valuation is Vi dollars per unit. So this is the bid signal given by a buyer. And a seller signal is of the following kind. So he says that I'm willing to offer up to sigma j units of some good Lj, and I want at least Aj dollars per unit, when let's say his true cost is Cj dollars per unit. Okay. So once these bid signals are obtained from the buyers and sellers, then what this mechanism does is that it determines an allocation which maximizes trading surplus subject to the flow constraint. And so here, so the first term here is, it's like the total utility delivered obtained by the buyers, and the second term here is like the total cost incurred by the sellers, and so this is like the trading surplus. And the constraint here is the flow constraint, or the demand less than equal to supply constraint on each link. So this is how the allocations are determined. Okay. Now the way the prices are determined is the following. So we look at all, for each link we look at all the sellers whose bids have been accepted, and we take the highest ask bid among those as the price on the link or the good. So this is how the prices are determined. Now the payment to be made by a buyer is simply the sum of prices on the links in his route or on the goods in his bundle times the quantity, and the payment to be made to a seller is simply the price on the good that he offers times the quantity. So as you can imagine, this mechanism is budget balanced by design. That is, the sum of payments that are made by the buyers exactly equals the sum of payments made to the sellers. So is there any question at this point? Should I slow down or?
Just to be sure, the sellers only sells.
They sell individual. They don't sell bundles. And the reason for that is that so here I'm trying to design a market mechanism in which uniform prices are determined. So if you have bundles on the seller side, then it becomes difficult to determine a uniform price for the good. So that is why the sellers can only sell individual goods. I mean, they can sell multiple units, but they cannot sell bundles.
But the buyers are looking for.
But buyers are looking for bundles. So for the buyers, it's either all or none. So they specify I want ABC, and then they must get either 1 unit of ABC or 2 units of ABC or nothing. Yeah. Okay. Now let me show you a simple example, and then we can get some understanding of how this mechanism actually works. So let's say we have just one good, and there are 3 buyers, and these have valuations, these have valuations 1.1, 2.1 and 3.1 for 1 unit each. And then there are 3 sellers, and they have costs 1, 2 and 3 per unit. Okay. And now let's say that these buyers make exactly these bids, and these sellers bid exactly their true costs. Now the way now the way the mechanism works is the following. So it will first look at the highest buy bid, which is 3.1, and the lowest sell bid, which is 1. And if the surplus is positive, then these are accepted. Then it looks at the next highest buy bid, which is 2.1, and the next lowest sell bid, which is 2. Again, if the trading surplus is positive, then these are accepted. Then it looks at the next highest buy bid and the next lowest sell bid, but then in this case the trading surplus ends up being negative, so these won't be accepted. Okay. So the mechanism would accept the highest 2 buy bids and the lowest 2 sell bids, and in this way it would be able to maximize the trading surplus.
This is how the stock market used to work several years ago, right? Like this, I mean, this is on a single commodity.
This is a single commodity, right? Right.
So I think this is the way the stock market used to clear. The clearance of the stock market was like that. People are providing some prices to sell stocks, and people are asking to buy stocks and according to pricing.
So the price was determined like this?
Yeah, but I don't think now it's different. It used to be like
It's
that.
still working
Okay.
today. Look at islt.com.
Oh, it's still this way today?
Electronically, but same thing. You can see a movie on islt.com.
Because I thought that now it's this is like a multi-party thing, and now it's one-to-one. Now it's not like okay, maybe.
Okay, I'm not completely sure of that, but I'll take your word for that. So, but what I'm trying to do here is create a sort of a combinatorial multilateral environment for exchange. So there are multiple goods, and moreover there is a bundle nature here. Okay, so here the first 2 buyers and the first 2 sellers are matched, and the way the price is determined is it's the highest ask price among the sellers whose bids have been accepted, and here the sellers with accepted bids are 1 and 2, and the highest among those is 2. So that's the price. So this is what these 2 buyers will get, even though they bid 3.1 and 2.1, and this is what these 2 sellers, sorry, this is what they will pay, and this is what they will get, these 2 sellers will get. So the thing to keep in mind here is that here the bids of the buyers and sellers, so the buyers bid their true valuations and the seller bid their true costs, and the corresponding allocation that was determined by this mechanism is the one that maximizes social welfare. So it is efficient. However, this may not be the case if the players are strategic. So in that case, they need not bid their true valuations or true costs. And the question in that case is, okay, what will happen in that case? What kind of outcome can we expect from this mechanism? Okay, so before I go on to that, let me give a very, since not everybody might be familiar with mechanism design, let me just give one slide quick overview of mechanism design. So we'll say that an auction mechanism is ex post individual rational if the utility derived from any outcome is non-negative for all agents. That is, no agent loses by participating in the auction. And we'll say that it is efficient if it maximizes social welfare, which if there are only buyers, then that would be the sum of utilities of all the agents. Though in our case, it is the sum of utility functions of the buyers minus the sum of the cost functions of all the sellers. And we'll say that the mechanism is incentive compatible if at equilibrium it is a dominant strategy for all the agents to truthfully reveal their true valuations and true cost functions.
Why do you need an equilibrium? Not always?
Because, well, I mean, equilibrium is in a market, the outcome would be the equilibrium outcome. So we only care about the equilibrium outcome, not the other outcomes. The other outcomes are not likely anyways. And the reason for wanting dominant strategy is, so dominant strategy means that independent of what other players are doing. It is a dominant strategy for a player to do something, and so in that case, a player does not need to worry about what other players are doing. So a dominant strategy implementation is considered very desirable for that reason. But actually is a very strong requirement, and it need not be achievable in all cases. And the fourth property that we would like a mechanism to have is that the sum of payments made by all the buyers equals sum of the payments made to all the sellers, or at the very least, there should not be a deficit. So the auctioneer should not have to put in money to make the system work. So at the very least, we would like the mechanism to have such a property. Okay, so now one of the most well-known class of mechanism is the Vickrey-Clark-Groves class of mechanisms, and this was introduced by Vickrey in '61, and he in fact got the Nobel Prize for this a few years ago. And it's well known that this class of mechanisms, they are incentive compatible, they are ex post individual rational, and they are efficient, but they are not budget balanced. So they have 3 of the 4 desirable properties, but they don't have budget balance. And moreover, there are a lot of variations of the VCG class of mechanisms, and what one notices is that in designing double-sided mechanisms, there is a lot of tension between efficiency and budget balance. So it is typically very hard to achieve both efficiency and budget balance at the same time. And in fact, there is a fundamental result due to Hurwitz, which says that in fact it is impossible to achieve all the 4 properties.
In general or in every setting?
No, this is a very particular environment. So quasi-linear simple exchange environment. Yeah. Okay, so now the question is, okay, which of these 4 properties our mechanism has? And so let's say that the buyers bid some B star and the seller bids some A star, and this results in some allocation X star Y star and some prices. And the pairs are strategic, and a buyer's payoff is his true valuation minus the per unit payment that he makes times the quantity. And a seller's payoff is the payment that he gets minus the per unit cost, sorry, not the payment, the price, per unit price minus the cost times the quantity. So that's a seller's profit or payoff. And again, here a Nash equilibrium is the usual one. So given that all the other players play equilibrium strategy, a particular player's payoff is maximized if he also uses the equilibrium strategy. Okay, so now let's go back to our example and see what's happening there. So again, just one good, and there are 3 buyers with the true valuations 3.1, 2.1, and 1.1, and again 3 sellers with costs 1, 2, 3. And let's say now these players are strategic and they need not bid their true valuations and true costs. So in that case, we would like to know what is the outcome, what kind of allocation results, and what is the equilibrium. Okay, so now, so let's say that all the buyers bid their true valuation. That is, buyers bid 3.1, 2.1, and 1.1, and seller 1 and seller 3 bid their true costs, but seller 2, whose true cost is 2, bids 2.1. So let's consider this as a candidate Nash equilibrium. So now let's look at, so given these bids, so what the mechanism will do is it will first look at the highest buyer bid and the lowest sell bid, and this has positive trading surplus, so these will be accepted. Then it looks at the next highest buy bid and the next lowest sell bid, and the trading surplus here is non-negative, so these are accepted. And then it looks at the next highest sell bid and the next next highest buy bid and the next lowest sell bid, but this will have negative trading surplus, so these are not accepted. So again here the highest two buy bids and the lowest two sell bids are accepted, and that's the same outcome as in the case when they were truthful. So now let's check that this set of strategies is a Nash equilibrium. So so let's consider the buyer with who bids 3.1. So he bids 3.1 and he gets allocation 1, and in fact he pays a price 2.1 because that's the highest price among the sellers whose bids are accepted. So he has a net surplus of 1. Now he clearly has no incentive to bid more than 3.1. So his payoff is not going to change, and in fact he turns out that he has no incentive to bid lower than 3.1 either, because if he bids below 2.1 then his bid won't be accepted and he will get net payoff 0. So he has no incentive to deviate from bidding 3.1. And now let's look at the next buyer who bids 2.1. If he bids, clearly again he has so he bids 2.1 and he gets, let's say he bids 2.1 and he gets allocation 1, and clearly he has no incentive to bid higher, and if he bids below 2.1 then he will get allocation 0 and he gets payoff 0. Now let's consider buyer 3. So he bids 1.1 and he gets 0 allocation, and if he wants anything, he wants to get a positive allocation, then he must bid above 2.1, but then he would end up paying a price 2.1 and he will get a negative payoff of -1. And so clearly he also has no incentive to deviate from bidding 1.1. Now let's consider the sellers. So seller, let's consider seller 1. So his true cost is 1 and that's exactly what he bids, and he gets 2.1, so he ends up with a payoff of 1.1. And if he clearly has no incentive to bid below 1, and if he bids higher than 1 and if he bids above 2.1, then he will end up with 0 allocation and so 0 payoff. So his payoff is maximized if he bids below 2.1, and so he has no incentive to deviate from bidding 1. Is there any question? And now let's consider seller 3. So his true cost is 3 and that's what he bids, and he gets 0 allocation. And if he wants to get a positive allocation, then he must bid below 3, but then he will end up getting a price 2.1, and that he would end up with the payoff of minus 0.9. So we'll have to sell below the true cost. So clearly he also has no incentive to deviate from bidding other than 3. Now let's look at seller 2. Seller 2 has true cost 2 and he bids 2.1. If he bids above 2.1, then he will his bid won't be accepted and he'll get 0 allocation and 0 payoff. And if he bids a little bit below 2.1, then his payoff will decrease. So his payoff is maximized if he bids exactly 2.1. So that means that this set of bid strategies is a Nash equilibrium. And moreover, as I argued before, the corresponding allocation is efficient. It maximizes social welfare.
Any value between the highest ask price to the lowest suggested price, whatever, maybe the opposite.
Right. Very good question, and so that would also be a Nash equilibrium. So here I said 2.1, but if these two, so any price between 2 and 2.1, if both these buyer and this seller bid that common price, then that will be a Nash equilibrium. So there are multiple Nash equilibria. That is true. But the interesting thing is that that still results in the efficient allocation. Corresponding allocation is still efficient, and in fact it can be shown that so even that is not the only set of Nash equilibria. There are other Nash equilibria, but what one can argue is that every Nash equilibrium allocation would be efficient. And so here I argued only a simple case, simple example with 3 buyers and 3 sellers and 1 good. But it turns out that now one can generalize this to arbitrary number of buyers and sellers and multiple goods, where buyers want bundles of goods and sellers sell individual goods. And the mechanism, as I said before, it's a budget balance by design, and it's also exposed individual rational. And there is a Nash equilibrium where all players except the highest math seller on each link bids truthfully. So this mechanism it's not incentive compatible, but in some very weak sense one could say that it is almost incentive compatible.
What is the cost of truthfulness? I mean, how much untruthful does the highest bidder bid?
How much does the highest, sorry?
So the highest match builder doesn't bid necessary truthful, right?
Yeah, so one can characterize that. So in this particular case, so if this buyer bids 2.1, then this seller will not bid above 2.1. So one can characterize that. One can say exactly what his strategy would be.
It's precisely the gap between
It's
the two numbers.
Right.
This is how
Right.
it's
Right.
precise.
Right. In fact, it will be the minimum of B2 and A3. So you can have another example where A3 is below B2, then A2 will be exactly A3. But more importantly, this mechanism has 0 price of anarchy, or price of anarchy is 1. So there is 0 efficiency loss. And the other thing probably worth pointing out here is that this is a non-VCG type mechanism, which is budget balanced, it's exposed to individual rational, and it is efficient, though it is not incentive compatible. And this mechanism is what is said to be a strong Nash implementation instead of a dominant strategy implementation. Okay, so here I assumed that all the players have complete information. So all the players know the true valuations and costs of others. So this is really a strong Nash implementation with full information. But then that may not be reasonable in certain auction settings. And so then the question becomes, what happens if the players have incomplete information? So let's consider that case. So let's say players have incomplete information, and there are n buyers and n sellers, and just to keep things simple, let's say they make unit demands on offers. And so what is known is that a seller's costs come from some distribution f, and a buyer's valuations come from some distribution g. So this is common knowledge. And now, since there is incomplete information, so we'll consider a Bayesian Nash equilibrium. So each player, instead of maximizing his payoff, maximizes its expected payoff. And moreover, let's say that moreover, we'll consider that all the sellers use the same strategy alpha as a function of their true cost, and all the buyers use the same strategy beta as a function of their true valuation. So their bids would be different because their costs are different, but the strategy functions that they use, let's say that is common. And furthermore, we'll consider those strategies which are ex post individual rational, in the sense that a seller bids at least his true cost and a buyer bids at most his true valuation. So a seller does not bid below his true cost, and buyer does not bid above his true valuation. And okay, so now in this context, now the question is, does a Bayesian Nash equilibrium exist? And if it does, then what happens to the outcome? Is it efficient or not? So what we can show is that if we fix the strategy used by the sellers to be some alpha and see what the response of the buyers is, then we can show that the buyers would respond with the strategy beta such that it is at least the true valuation. So they would have a tendency to bid the true valuation or higher. And that is a bit counterintuitive. But the reason for that is that the way this mechanism works, the prices and the payments are being determined by the bids of the sellers. So a buyer, by bidding higher, is actually able to maximize his expected payoff, because the probability of the bid being accepted becomes higher. And now let's look at the case where the buyers bid truthfully and the sellers respond with some alpha n. And so we can characterize the response function of the sellers, and what we can show is that this the response function of the sellers would converge to the truth-telling function in the supernorm as n goes to infinity, as the number of players goes to infinity. And a very rough intuition for this is that as there are more and more players, so there's more competition, and this forces the sellers to be truthful. But that's a very rough intuition. And now putting these two things together, one can argue that a Bayesian Nash equilibrium exists, and moreover, any symmetric Bayesian Nash equilibrium will converge to truth-telling strategies. And so we have a mechanism which is budget balanced by design, and moreover, this mechanism, it is in the incomplete information case, it is asymptotically Bayesian incentive compatible, and hence it is asymptotically efficient.
Isn't that too strong an assumption in this case, that just because there are more number of players, the sellers are becoming more and more truthful, and we don't see that in the real world? For example, car dealers are not really truthful. There are too many cars available, and on the auction sites, it's not necessary that you may have multiple commodities and multiple sellers, but they don't necessarily converge to
Car dealers are not rational. Here you see only there is a probability distribution. So if you have more, more players, then things are becoming more and more close to each other.
That's right. Right. So this is what one would expect, but it's not. It's not a given. I mean, it could happen some other way, but so this needs to be shown. And it turns out that as you have a lot bigger and bigger market, then the players would tend to become truthful. But it's not. I mean, it's not something you can take as a fait accompli. I mean, it needs to be shown. Okay, so okay, so now all these results, all these results from theory and equilibrium analysis are fine, but then the real question is what happens in a real market? I mean, how will this mechanism really work in a real auction setting? And if it will work, then how will it perform? So to test that, so we implemented this mechanism, and we had a software test bed, and then we used this software test bed to conduct experiments, and we had students participate in these experiments. And so these students were told what their true utility functions are and what their true cost functions are, and they were given monetary rewards depending on how well they performed in the experiment.
Was it real money?
Yes, real money. They were told, they were told the formula. So if you generate this much surplus, you'll get this much money. There was some participation money which everybody got, and then depending on how well they performed, they got a certain reward. And so we conducted a series of these experiments. And so what we observed was that this mechanism had about 80% efficiency with 4 buyers and 4 sellers. And so I might say that that's sort of compatible with the asymptotic result. So the asymptotics have not kicked in yet. And hopefully, if this experiment is conducted with larger number of players, then the efficiency observed would increase.
How did you prevent collusion?
Oh, it's a very controlled environment, so they are not allowed to talk, and the laptop that they're given, so they cannot communicate with that laptop unless they were using some other gestures as a way of signaling. But this was done in a very controlled environment, to the best we could. Of course.
But wait, they can't go. I mean, what if they go? What is the next day? Can't they talk the day before to collude?
Well, that's a very good question. We didn't worry about that. So we didn't really tell the participants who so we invited applications, and then we chose 8 participants, but we did not tell who each of them who all would be coming. So hopefully that eliminates some of the possibilities of collusion.
What kind of real money were you giving? Something which matters to them, or just a game?
Well, we had, so for the one experiment we had $500 to divide between the 8 participants. So it was fixed, and then depending on, so there was competition between them.
And how long did that play for it?
This whole session lasted about 3 hours. Yeah. So it's not a perfect experiment. I mean, it's still, there are a lot of things that can go wrong, and they did. But the point of such an experiment is to get an idea of how well it will work. I mean, we're doing a lot of Nash Equilibrium analysis and a lot of Bayesian Nash analysis, but we typically, for mechanism, there is very little understanding of is it actually going to work in practice or not. So that's what we try to get from this, and we're not trying to benchmark the performance of the mechanism per se from these experiments.
Did they know the distribution of the cost functions?
They were told the distribution. So yes, that's right. They were told, okay, this is the distribution, and yeah.
Did they have experience in experiments like that?
Sorry?
Did they have experience?
Yeah, so what we did was we did some learning rounds where their performance was not counted, so just to bring everybody on par. We had a few rounds where they could just experiment and learn. And okay, so let me quickly mention some related work. So there's a lot of effort of late, particularly in the networking community, on auction design for divisible capacity networks. And one of the main mechanisms is the one proposed by Kelly, which was shown to achieve efficient allocation when the agents are non-strategic and act as price takers. And it was shown that this mechanism, when the agents are strategic, can result in up to 25% loss in efficiency in a single link network, and there can be a full efficiency loss in a general network. And there's been a lot of work along these lines, and many extensions have been proposed to fix the original mechanism. And I also have a mechanism for allocation of divisible capacity networks. And so if there's any interest, I can talk about that later. And to summarize, so what I've done is I introduced a market mechanism for decentralized allocation of goods and services as application for various things. And the proposed mechanism, it's budget balanced by design, and it's a strong Nash implementation. And with complete information, every outcome is efficient. But with incomplete information, it is only asymptotically efficient. And moreover, we conducted human subject experiments, which suggests that it performs reasonably well in practice. Well, there I have had a simple supply chain setting in mind, though the actual supply chains tend to be very, very complicated. So if you imagine just one stage supply chain network, so auto manufacturers on one side and then the OEMs on the other side. So it's a two-sided market. So that's what I mean here. But the actual supply chain is a lot more complex. So there one would need elaboration of this mechanism.